All right. So hello everyone. Hello again. So today is the lecture number 2, and we start this lecture with discussing or recalling the topic of complex functions. Complex functions. So this is the topic 1.3, I guess. I believe. All right. So complex functions, complex numbers. So I remind you that so basically when we're talking about the real valued numbers, we can put them on one axis. Let's call it axis X, and denoted that this is real numbers. So all real numbers can be placed on this axis, including 0, 1, -1, and all other types of numbers, including irrational, 0.1, pi, somewhere here. All right, so and this is the type of numbers that we used to, but if you think about this a little bit more, you will acknowledge that even this negative part of this axis, these negative numbers, they already hard to meet in actual life, right? So it's hard to come up with an example of negative numbers in real life, except for some economical bank accounts, these artificial things, right? We can easily live without negative numbers, or I mean, people used to live without negative numbers. But at some point we invented them, and they became very useful. And in particular, the negative numbers allowed us to create electrodynamics, right? Because electrodynamics is all based on charges of two kinds, of positive, negative charges, and this concept of negative numbers become very, very useful. But it turns out that it's not enough to have only real numbers, and for engineering specifically, we need these complex numbers. And of course, you are aware of them. I'm just remind you what it is and how it looks like. So let's suppose we have the orthogonal axis to the axis X, and we instead of 1 on real X, we use the unit called I here, and we denote this, yes, and of course minus I here, and we denote or name this axis Y imaginary numbers. So real numbers, imaginary numbers. And the unit is I, and I is interesting thing. We postulate that I is equal to square root of -1, so that the I squared gives us minus 1. So this is unusual, right? For people who never dealt with complex numbers, because the square of any number, we used to the fact that the square of any number gives us positive plus something. In this case, it is equal to -1. And in this sense, it's already a little bit unusual. So by continuing these numbers to this plane, to the entire plane, we call this complex plane of numbers. So this entire plane is complex plane, and we can pick any point in this complex plane and name this z, and this z will get the real number x and the imaginary number y times I, right? Because 1 is on this axis is I, so the length on the axis y is y times I, and as a result, this complex number z is given by x plus I times y. In what follows, I won't write this dot between I and y. So this is the xy representation of complex number. So let's consider another representation, which is called polar representation. To do so, let's draw a line from the origin to this point z, and the distance from origin to point z is denoted by absolute value of z. So this is the length of this line, and of course we need another parameter, not only modulus z, because we can, for example, rotate this line around. So we need also this angle phi, which we count from the axis x. So this is angle phi. Okay. So on the other hand, by drawing, by putting the perpendicular from the point z to the x, we get this right triangle with two legs, leg x, leg y, and the hypotenuse modulus z, right? So considering this right triangle, we conclude that the cosine phi, it is leg x, right? So it's x over hypotenuse modulus z, and the same for the sine phi. It's given by y over z. Okay, so let's derive x and y from these formulas and plug in them to this one, to the xy representation of the complex number. So after that, it's very easy to do, right? So after that, we get z. Modulus z is common, so we can get it from the parenthesis. And in the parenthesis, we get cosine phi plus I sine phi. Let's frame this formula. Let's frame this formula. All right. So what is left unknown is angle. Yeah, we need to divide this modulus z and angle phi. So in order to define this modulus z, let's first discuss the concept of complex conjugation. So the complex number, let me just rewrite it here. Z equals x plus I y, right? We introduce the counterpart to this number, which we call complex conjugate, or just conjugate number, z star, and it's equal to basically the same, but up to the change of the sign before the imaginary unit, I, y. So why we need this complex conjugation? We need it for many reasons. In electrodynamics, electrical engineering, it denotes the signal with with the opposite frequency, and it also denotes the phase delay, etc. But for now, for this part, let's consider a product of the two. So let's consider the product of z times z star, right? So what it is? It is x plus iy times x minus y, iy minus iy. Okay, so we can so it's equal to x squared, right? Minus iy squared, which is equal to x squared plus y squared. Very good. So this is let's denote it by star, and let's return to these two formulas for sine and cosine, and recall that if we square each of them, so we get cosine square phi equals x squared over modulus z squared, and sine square phi equals to y squared over z squared. And take the sum of the two, we got sine square phi plus cosine square phi. And for two-dimensional space, it always equals to 1, as we know that. So that means that x squared over z squared plus y squared over modulus z squared is equal to 1. And if we multiply both parts by modulus z squared, we get x squared plus y squared equals 2 modulus z squared. So this is basically the formula that allows us to find the modulus, the absolute value of the complex number from the real and imaginary part of this number. So it's going to be square root from x squared plus y squared. So far, so good. Let's denote it by the double star like this. And now let's compare these two formulas. So for this product, we got this construction, x squared plus y squared. And from this formula, we got the same equal to modulus z squared. That means that, or we conclude that, the z times z squared, the z star, is equal to modulus z squared. Right? So the conclusion is simple. The conclusion is the complex conjugated number, complex number, is it allows us to find the absolute value of the complex number by taking the product of the number by its complex conjugated counterpart. All right. So what's next? What would we get if we take the sum of the complex number and complex conjugated number? So from this formula, x plus iy plus x minus iy, we get, so I and minus iy minus iy cancel out, and we get 2x, which is real part, twice real part. So the x, the real part of the number, is equal to z plus z star over 2. So this formula allows to calculate the real part of the complex number. And to do so, you just need to take this number, add the complex conjugated version of that number, and divide by 2. and you by doing that you get this real part of the number. What would we get if we subtract that? Z minus Z star. I mean, of course, we get 2IY, and we conclude that Y, which is imaginary part of the complex number, is given by Z minus Z star over 2I. So in order to define the imaginary part of the complex number, we need to subtract the complex conjugated number from the itself and divide it by 2I. So let me, X is a real part of Z, Y is imaginary part of Z. Very good. So, and now we introduce very exceptionally important formula. It's called Euler's formula. Euler's formula. So without the proof, because the proof needs some knowledge from the theory of series, I just bring this formula here. So the formula states the connection between exponential function of I times phi. Phi is the angle, I is the imaginary unit. And it's equal to cosine this angle phi plus I sine angle phi. So let us frame this formula as it's so important. Yeah, it's very important formula for the what follows. I mean, for example, what would we get if the phi is equal to 0, right? So in this case, cosine 0 is equal to 1. Sine 0 gives us 0. So e to the power of basically 0 equals 1. Nothing is interesting. What would we get if phi is equal to pi over 2? Yeah. Guys, please keep your mics muted. So e to the power of I pi over 2. So phi is equal to pi over 2. So in this case, cosine pi over 2 is equal to 0. Sine pi over 2 is 1. So it's equal to imaginary unit, right? What would I get if I substitute I by minus I here? Write something like this. Cosine phi minus I sine phi, right? So this is the complex conjugated version of the Euler's formula, because this is real, so it's a complex number, and the difference is that we put minus here in this formula before the I, so it's a complex conjugated version of the Euler's formula, which means that in order to take the complex conjugation of this exponential function, again, we just can substitute I by 2 minus I, or put minus I before I. Right. And we know that the product of z of the complex number and its conjugated version gives us the absolute value squared. So what would we get if we take I to the power of I phi and make times the complex conjugated version I phi? So I'm supposed to get the modulus of EI phi, right? And from this part, I get e to the power of I phi minus I phi, so it's e to the power of 0, so it is 1. So basically this exponential function is nothing but the complex number with absolute value 1. Absolute value 1. So let me maybe summarize 3 versions we denote or we can use to represent a complex number. So first of all, it can be XY representation, right? The next one is polar representation with the modulus Z times cosine phi plus I sine phi. And from this part, we can use the Euler's formula to substitute this part by the exponential function. So we get the exponential representation of the complex number of any complex number. So it's equal to the modulus Z times exponential function I to the power of phi. Okay. So technically, using these complex functions is very useful because as we remember, the derivative of exponential function is just the function itself, right? And derivative of exponential function with something like a constant times x is equal to a and then this complex function. So taking derivatives and also the integrals of exponential functions is very, very simple. For example, for this complex number, if we take the derivative by angle phi, we get this absolute value is just constant, right? And then the derivative of this exponential function by phi, which gives us I, and then the exponential function I phi itself. Yeah. So instead of taking the derivative of this sine, cosine, etc., it becomes very, very simple. And especially if you have multiple terms with many complex numbers, so taking the derivative of complex number in the exponential representation is very, very useful. So in the electrical engineering, we often use this concept of phasors. And let me introduce that at this point. So like a site by another color. So in electrical engineering, we use phasors. Phasors. What is a phasor? So suppose I have an electric field. It can be voltage, current, whatever. Just some function that depends on time as a cosine or sine function. Let's put cosine omega t plus some phi, some node. Right. So this is this is something that we call either sinusoidal function or monochromatic monochromatic field. Monochromatic field, term monochromatic means mono means single frequency. So it's a single frequency signal that is oscillating like this, right? Like a sinusoidal or cosinusoidal function. And again, when we do the things, when we do the operations with this function, it's not very easy to keep track of this cosine. Often it's better to replace this cosine with exponential function. And how we do so? So from so from Euler's formula, right, this I to the power of phi, it's equal to cosine phi plus I sine phi. So cosine phi in this formula is real part of e to the power of I phi. Okay, and I need this cosine function, so I can use this approach of taking the sum of the two and divide by 2 to get the real value of this exponential function. So this formula gives me cosine phi is equal to e to the power of I phi plus e to the power of complex conjugated version minus I phi divided by 2. Okay, so I can substitute this cosine to this formula now. And what I get? I would get e of t is equal to 1 over 2 e naught e sub 0 e to the power of I omega t plus phi sub 0, and plus basically the same. So this 1 over 2 comes from these two in the denominator. Right. And basically the same but complex conjugated. So we usually write this plus and then complex conjugated. CC, complex conjugate. So instead of this formula with cosine, I can use this one, but this is not the end, because we got the formula with two terms, and this term comes with plus omega, so we denote it by e plus, something like this. And this one will give us minus I omega t, which is essentially the minus omega term. So it's e minus. And and for the analysis, we can write just one part of this formula, e plus, and that is sufficient for all the calculations. So let me show you that. So this basically means that we can write the electric field as a function of time in this way. So it will be e sub 0 e to the power of I omega t plus phi sub 0. Okay. So I do all the calculations and got the field in this form, like some absolute some amplitude, because I remind you that the modulus of this one is 1. So this e sub 0 is the amplitude of the field, and the second term gives the phase of the field. right? And then after getting the result in this way, I can I can find the real part of this one. What would I get? I would get sorry, E plus, right? I mean, it doesn't matter. Let's not write it here. So E plus E complex conjugated over 2. And this is exactly this formula. This is exactly this formula here. Okay. So once again, for all the calculations, when I am dealing with single frequency signal, like a sinusoidal signal, I can I can use for my calculations this exponential representation of the signal. And then for the final result, I will just need to take the real part of this, of the result. Do you have any questions at this time? Yeah, so once again, if you got any questions, don't hesitate to ask your questions. All right, and for example, I measure some volume or some voltage. So it's a voltage in some circuit, right, as a function of time, and I get something like V sub 0 e to the power of I omega t plus phi 0. I can rewrite this by factorizing this phase here, this term, as V sub 0 e to the power of I phi sub 0, right? So that's the second term, times e to the power of I omega t, right? So this part here, it contains the amplitude of the signal of this voltage and the initial phase of this voltage, and this part is called phasor. So this is phasor of the field, and the second part is just harmonic function, just harmonic function. Okay, so let us make a quick break at this point. So now let's consider a couple of number of problems. So the first one, first problem. So let's express e to the power of I pi over 3 in the xy representation. So basically convert this e to the power of I pi over 3 to the xy representation. So we know that e to the power of I phi is equal to cosine phi plus I sine phi, Euler's formula, right? And let's substitute the phi for pi over 3. Pi over 3 is equal to cosine pi over 3 plus I sine pi over 3. All right, cosine pi over 3, as far as I remember, that's 1 over 2. And plus I sine pi over 3 then is equal to minus square root of 3 over 2. Something like this. So that's the answer. X is equal to 1 over 2 the y is equal to square root of 3 over 2. Pretty simple. Okay, let's consider another problem. Problem 2. So for a given complex number z, 3 minus 4i, find absolute value z and angle phi. So what is absolute value z and angle phi? So for the absolute value, it's very simple. So we know that absolute value squared is given by z times z complex conjugated. It's equal to 3 minus 4i times 3 plus 4i, right? And it's equal to 9 plus 16 is equal to 25. So the absolute value z is equal to 5, square root of 22 to 25. All right. So for the phi, oh, I probably forgot to define this phi, but yeah, let's derive it now. So we know that cosine phi is equal to x over modulus z, right? And sine phi is equal to y over modulus z. So let's divide sine by cosine. So after that, the modulus z is gone, and we get y over x is equal to tangent phi. And that means that in order to find phi, I use arc tangent y over x. We can frame this formula too, because it was actually the part of the discussion above. Yeah, so in order to find the angle phi in this polar representation of complex number, we just need to calculate the arctangents y over x. Arctangent y over x. Y is the imaginary, x is the real part. So in our case, for this z equal 3 minus 4i, the phi is equal to arctangent y is minus 4, x is 3. I don't know what it is. One can use any of these calculators, online calculator to find the number. So it's gonna be minus something, minus, I guess, 60 or 70 degrees. All right, so next problem number 3. Let's take one from, a similar one from your homework. For example, this one, they compute the inner product of two complex vectors. But let's change let's select other vectors. So inner product or dot product, right? Of two vectors. Let's pick one vector A to be 1 and 1 plus I. So the first component, or x component, is 1. The second component is 1 plus I. And B, let's make it 2 plus I and 2 minus I. Something like this. So how we find the inner product? So when we calculate the inner product, that's just the sum of the products of the corresponding components, x by x, y by y, z by z. All right. And we can write the same as this construction. So if I take the first one as a row in a row representation, this vector 1, and the second component is 1 plus I, right? And the product of the second vector 2 plus I over 2 minus I, right? So why I do so? Because writing this way, I can use this useful matrix multiplication approach when I take the first element, multiply by the first element from the first, in the row of the first vector, multiplied by the first element in the column in the second vector, and then plus the second element times the second element. This is trivial for the vectors, but important for the matrices. So what I get 2 plus I for the first one times 1 plus 1 plus I times 2 minus I. What would I get? 2 plus I plus 1 times 2 gives me 2, then minus I, then plus 2I, and then plus I and minus I gives me minus I squared, which is plus 1. Plus 1. Right, so this I here cancel out. This 2 and 1 gives 5. So the result is 5 plus 2I. 5 plus 2I. So as you can see, the inner product of two vectors of complex vectors is equal to just a scalar. If it's not specifically mentioned, for example, in the homework, right? I ask you to compute the inner product of two other complex vectors. Don't take the complex conjugate of one of them. Do the way I just done. All right, so okay, so I guess this is that's it about complex numbers and complex functions. And let's start discussing the field operators. So we have 1 hour or so. It's a good time to start field operators. The key topic for the rest of the course. So our course is about field analysis, right? Fields in electromagnetic devices. And the way how we analyze the fields in any device, we basically use these field operators. And I guess the best way is to introduce the field operators is to first introduce to you the nabla operator. So let me write it this way. In order to describe fields, these field operators work not only for electromagnetism. They also used for acoustics, for hydrodynamics, and for many other fields. All right. So in order to describe a field or fields, we introduce the nabla operator. Nabla operator. So it's denoted by this nabla. It's also known as del operator. Del. Nabla or del operator. So in what follows, we will use this word nabla to name this operator. So what is nabla operator? Nabla operator is a vector operator defined by this formula. So we have this nabla, and it's given by this formula. So the easiest, the most simple formula for this nabla operator is for the x, y, and z coordinates, the Cartesian coordinates, Cartesian coordinate system. So let's use it in that coordinate system, x, y, z. So for the x, y, z, we have I is the unit vector along coordinate x, and then this I is multiplied by d over dx. This is partial derivative by x. And let me actually write this part like this, so in color. By putting this parenthesis, I mean that this is, there is a space to plug in something there. So this operator operates on something or acts on something. So this nabla is not used by its own. It's always applied on something, on some function, some vector, and that's why I put this parenthesis, empty parenthesis there. And the same term for the j. So it's another so j vector times partial derivative by y, and finally k partial derivative by z. And again, we have to plug in something to this to this space in the empty parentheses. All right, so this is the formula, and pretty important one. So I put some this exclamation mark. So the nabla operator can be applied on a scalar or a vector function. Scalar or vector function, they both work. And hence we have 3 different cases. Let's consider them. So the first case is when I apply this scalar function. So I basically plug in f to this empty parenthesis, right? f is the function of, for example, coordinates. It's basically a function of the of coordinates, x, y, z. So f is scalar function of coordinates. Scalar function of coordinates. For example, it can be temperature, right? Like a like temperature in, for example, in my room, it's apparently colder at the floor, and it's getting warmer by the ceilings, and etc. So it's some function that fluctuates, changes as a function of coordinate. It can be potential. In electromagnetics, of course, we have this potential, so it's also another example of scalar function. And when nabla operator acts on the scalar function, we call this a gradient. Gradient. Oops, sorry, gradient. Yeah. Okay, another possibility here, if my function is a vector, but the nabla operator itself, as you can see, it's kind of a vector because it contains this I, j, and k, which are vectors. So the result is also a vector. So it's a vector operator, and I can apply a vector or vector operator on another vector, either inner product or dot product or cross product, as we discussed last week. So when I apply this nabla operator as a dot product, as we discussed, I would get a scalar, right? The result is a scalar function. And of course, A is a vector field. For example, E fields in our area, H fields, etc. So in this way, when nabla operator acts on a vector as a dot product, it's called divergence. Divergence. For the reason that will be clear, hopefully today. And the third operation possible when I apply this nabla operator as a cross nabla cross A. And as we discussed, the result will be a vector, another vector. And we call this a curl. For the reason that will be clear next week. So today we're gonna discuss this gradient and hopefully divergence, and continue about the curl next week. So let's discuss the gradient. A gradient. So to do so, let's pick up one function as a function. Function of coordinates x, y, z, for example, and plug in this function of coordinates to the nabla operator. All right. What will I get? So I get this I, and then times d over dx plus j d over dy plus k d over dz. This is for the nabla operator, and it acts on the function f. So I basically multiply this f on the each term in this nabla operator in this parenthesis. So I get I df over dx plus j df over dy plus k df over dz. Okay. So this is the formula for the gradient. So sometimes we denote gradient, or usually like this, the nabla function, but sometimes you can meet this grad f, or like this. So this is basically the same. And the formula, just let me repeat it here. dy plus k df over dz. Gradient. The gradient. So let's first discuss some properties of gradient, and then we will solve some problems. So for the first property of a gradient, let's state that gradient is connected with the differential. Gradient is connected with, or with the differential. Differential. Let's highlight this in color. So let's write the differential for this function f, x, y, z, right? So we recall this formula for the differential. It's given by this partial derivative by x dx plus partial derivative by y dy plus partial derivative by z dz. And I noticed that this line, this formula, this expression can be actually written as a product of two vectors. The first one is df over dx unit vector I plus df over dy unit vector j plus df over dz unit vector k, and this is first vector, and I multiply this by by I dx plus j dy plus k dz. So these two vectors. Why? Because when I take this product, for example, this term by this one, so I times I, the inner product of these two gives us 1. So the result will be dx or df over dx times dx. So we get this term here. But when I take the product of I and j, these two, the product is 0. So this we can omit this these terms, and you can see that we get this formula above for the differential. But look at this. So this term here is exactly the formula for the gradient. So this is the gradient of f. And this formula in the second parenthesis is given, is actually the differential of radius vector. Let me make a note on this. So what is differential of the radius vector? So suppose I have the coordinate system like this with the x, y, and z, right? With the unit vectors I, unit vector j, unit vector k, and a radius vector is a vector that points to the point of interest, right? Some arbitrary point with coordinates x, y, and z. X, y, and z. And then I said that I am interested in the field in the next point, some point located, for example, here with coordinates x plus dx, y plus dy, and z plus dz. Right, so it's a close point to the to the first one. Let me okay. Yeah, and this is the unit vector. Sorry, the radius vector in this point is given by this radius vector plus the change of the radius vector, right? It's easily to see to use this the summation rule for the vectors. So if I denote this small vector by dr, this small r, so the second vector is given by r plus dr. In the same time, we know that the radius vector is given by its coordinates x, y, and z plus y, j plus z, k. Right? And if I take the derivative or the differential using the formula, our first formula in the frame, what would I get? It is d. Let me write step by step. So it's dr over dx, dx plus dr over dy, dy plus dr over dz, dz, right? So dr over dx. So the second and third terms in the formula for r don't contain any x, so the derivative is 0, and the only first term which contains the x, and I take the derivative of this, x is gone, and I left with I, so I get I dx, and the same way for the second and third term, so I get j for d and dy plus k dz. So we got exactly this formula here, this second parenthesis. So this is dr. And we conclude, we come to quite important formula for the, which states that the differential of the scalar function is or can be represented by the gradient of this function times dr. Okay. I remind you that gradient is a vector, dr, of course, is a vector, and df is a scalar as a product of two, inner product of two vectors. So I guess this formula deserves to be put in a red frame. All right. So a differential of any scalar function can be represented by the gradient, and basically the scalar product of gradient with the differential of the radius vector. So the second property, important one, that states that the gradient is orthogonal to the level surface of the field. So let me, the gradient is orthogonal to a level surface. So what is a level surface? A level surface is the surface where the field is constant. It doesn't change. For example, the temperature in my room is, I mean, it's highly possible that the temperature in my room by the floor, by the level of the floor, is the same, right? It doesn't change over the floor. And of course, one can imagine many types of level surfaces. So the level surface of a field is the surface where field is constant. Is the surface where is the surface of constant field, is the surface of f constant. So if f is constant, that means that, I mean, I'm looking at this formula here for the differential. It means that the f is 0, right? If it doesn't change, the differential is 0 of this field. And that means that the gradient of this field times dr is equal to 0. And what it means? So this is the dot product of two vectors, and it is, I mean, or geometrically, it is a projection of gradient on the dr. And if I'm sitting on this surface, level surface, where f is constant, right, and change it from, I mean, from point to point in the surface. So this is my dr in the surface. The field doesn't change, and in this case, if I am on this surface, the gradient is orthogonal to the dr, because the gradient in this case must be orthogonal because the scalar product is 0. So this will be the gradient. So we conclude that the gradient of field is orthogonal to the level surface. Okay. I mean, for example, in electromagnetics, we have, for example, the charge, right? And the charge creates electric field and potential. We can use either potential or electric field to describe the field around the charge. And because of the spherical symmetry of the problem, the potential on this spherical surface is constant, right? And that means that the gradient of this potential is directed like this. It's normally to the surface of level surface. In this case, it's called either potential surface, so basically the surface of constant potential, and the corresponding gradient is directed like this, and the minus of this gradient of potential gives us the electric field, as we probably know. So in this case, the gradient allows us to connect the field, the potential, and the electric field. So far, so good. So the third property of a gradient states that the gradient of a scalar field points to the direction of the maximum rate of change of that field. Okay, so the field, of course, changes in space. It's a function of coordinate, and this change depends. I mean, the rate of this change is also function of the direction in the space. In some direction it changes faster. The temperature in my room changes very slowly in the XY direction, in the plane of the floor, but it can change more stronger or faster in the Z direction. And the use of gradient in this case is that gradient indicates the direction of the maximum rate of this change. So the gradient of a scalar field points to the direction of the maximum rate of change, rate of change of that field, of the field. Okay. So let's prove that. The proof is very simple. So let's consider a field, and the field is a function of coordinate of radius vector, right? And for this field, we can find the the gradient, which can be denoted by like this, right? So in this field, let's consider a unit vector. Consider a unit vector. Let's denote it by E. So unit vector in arbitrary direction, in arbitrary direction. And this, I mean, since this is a unit vector, the modulus this vector is 1. Modulus is 1. All right. So let's recall that the change of the field of the function is given by the gradient of this function times dr. And dr is the change in this, I mean the distance between two close points in this field. And of course we can write the same formula for the for the change of the field for a larger distance, for example, for this unit vector. So how much this field change in the direction of this unit vector. So the change of field F in this E direction, it's equal to this gradient of this field, right, times the vector E. Okay. Vector E. So at this point, we need to recall this Cauchy Schwarz theorem. It's called Cauchy Schwarz theorem. Cauchy Schwarz theorem. Very simple theorem, and actually we already mentioned this today. It basically states that if I have a inner product of two vectors like A and B, right, I can take the absolute value of this product of two vectors, and this absolute value of the product of two vectors is less than or equal to the product of the absolute values of each of the vectors. Right. So it's very easy to understand, because as we discussed, the inner product of two vectors is the projection of one vector on another one, like this vector A, this is vector B, and the projection of vector A and vector B would be this number here. So this is the modulus A times modulus B, and of course this projection is less than or equal to the product of the modulus of vector A times vector B, because the projection is always shorter than the vector itself. And the equal only when A and B collinear, when they lie on the same, basically, when they point in the same direction. Yeah, Cauchy-Schwarz theorem is pretty simple, but it allows us to take this, take the modulus of this modulus gradient F times unit vector E, and it's necessarily smaller than the modulus of gradient times the modulus of the vector E. And by the definition, the unit vector gets modulus 1. So it's equals to 1, which means that the modulus of gradient times E is less than the modulus of the gradient. Okay. And here it's important point here is that the maximal change of this modulus on the left is this change is maximal when this unit vector points collinear with this with the gradient, where they are co-directed, when they direct to the same point. And when that happens, when they point to the same direction, this change is given by the modulus. And let me write this. And when so this change, the change is modulus of the gradient. Okay, so gradient indicates the direction in space in which the field changes the most, with the maximum rate. And the rate, and this rate of this change is equal to the modulus of the gradient. This is quite important. And let's discuss the last property of the gradient. It's called gradient theorem. Gradient theorem. I put quotes because this is not standardized term. sometimes it's named gradient integral gradient theorem, something like this. This author this book I have, this David Griffiths, right? David Griffiths called this the gradient theorem. So the theorem states that, for example, if I'm interested in the integral of gradient between 2 points in in the space, let's call them P and Q, and I take the integral from one point to another point, right? So I integral this P and Q of the gradient in this field, so dr vector. So I substitute this gradient dr by the differential of f, as we already know. And when I take the integral of differential, I simply get the field itself, right? So it will be f in the point Q minus f in the point P. So this is basically the gradient theorem. So gradient theorem, let me rewrite this here from PQ, gradient f dr is equal to fq minus fp. In this way, it doesn't really, it's not really useful. It's more useful when you take, when P and Q points, they coincide. Basically, if you consider the integral like this over the closed loop, then this theorem states that this integral will be equal to 0 because f, basically in the same point, you subtract the same value, so you get 0. And when that happens, the field is called potential field. It is quite important type of the field. For example, our gravitational field is potential, right? And the electrostatic field also potential. So it's quite important in those areas. So now let's consider several problems just to to get used of this gradient. So let's consider problem 1. Let's take some function. For simplicity, let's go with 2 variables, x square plus y squared. Very simple. So what is gradient? Right. The gradient f, let me let me write this formula for the two variables. It's df over dxi plus df over dy j. Right. So I can go and apply this formula. So df over dx gives me 2x times I plus df over dy times j gives me 2y j. Okay, so this is the answer. This is the gradient. And I also can rewrite this vector in the column representation. So it's a 2x and 2y here. So it's a column representation of the same vector. All right, let's consider problem number 2. Problem 2. Let's take something like, the function x, y, and z. Let's take x times y times z. So what is gradient of this field? Again, the nabla f gives me the first derivative by x, so I get yz and times I, then plus the second by y, so I get x z times j, and then the third one is by z, so I get x times y times k, right? And again, in the column representation, it's given by yz, xz, xy. Okay, so this is the two ways of representing of the same vector, and this is the answer. As you can see, it's very easy to get. So the third problem number 3. Problem number 3. Let's take something a little bit more complex. X, y, and z. Square root of x squared plus y squared plus z squared. Practically useful problem. Again, find the gradient of this field. So in order to obtain the gradient of this field, we need to get the derivative by x by y by z. This x and y and z, they are symmetrically arranged in this formula. So when I get the derivative by x, I can write formulas for derivatives by y and by z automatically. So df over dx, x here is the complex function, is a function of a function. So I apply this chain rule, right? So I take the derivative by or as a square root function. So I get 1 over 2, and the power is minus 1 over 2. So I write this like 1 over square root of x squared plus y squared plus z squared. And I have to multiply this by the derivative of x squared by x, which is 2x. So the answer is x over x squared, y squared, z squared. Okay, and as I said, the derivative of f by y is essentially the same, but up to replacing x by y in the numerator, and the rest is the same. And it's the same. Likewise for the z. I get z here, and x squared, y squared, z squared in the denominator. Okay, and so I'm all set. I mean, I'm ready to write the formula, the final result for the gradient. So the denominator, all these three terms is the same, so I can make it common. X squared, y squared, z squared. And the numerator is given by x times I plus y times j plus z times k vector. Yeah. So this is the answer. So do you have any questions by this time, at this moment? Okay. So let me consider the problem number 4. And this is the temperature problem. So let's assume that the temperature in a plane is distributed temperature in the plane is given by t, x, and y, and the function would be like x to the power of 3 minus 3x xy squared. So let's define the gradient of this temperature distribution. Let's obtain this temperature gradient in a particular point, like point 1, minus 1, 1. And direction of the maximum change of the temperature in that point, in the minus 1 and 1 point. Okay, so procedure is the same. The gradient of this temperature field is given by the x derivative of this function, which is 2x squared. Oh, sorry, 3x squared minus 3y squared. Okay, so this is the x component of the gradient. And for the y, it is given by the derivative by y, which is minus 3x. So 3 times 2 is 6, and y times j. Right. So this is the gradient distribution in the same field, and it also changes from point to point. And what is the gradient in point minus 1 and 1? So let's substitute minus 1 for x, 1 for y is given by 3 minus 3 I, so it's going to be 0, minus plus 6 plus 6j. Okay, so the answer is 0 times I plus 6 times j. Okay, and the modulus of this gradient in point 1 minus 1 1 is equal to 6. So the direction of the maximum rate of change of temperature at the point minus 1 and 1 is along the axis y, and the change is equal to 6. And this is maximum change in this field. In this field and in this particular point. If I would substitute, if I would consider the field in another point, I mean the gradient of the field in another point, let's say 2 and 1, then the first term would also survive, and the maximum change of the temperature would be directed to some direction in this plane. All right, so do you have any questions regarding this part? If not, let me start the discussion about divergence. I remind you, this is the second possible operation with the nabla operator. When I apply my nabla operator to a vector, and yeah, and I apply this like an inner product, right? Inner. So I have vector A, let's say, nabla operator, apply to this vector A like this. So this is basically the divergence. It's also sometimes also denoted by this divergence A. This is basically the same. So importance of divergence, why we need divergence. So in contrast to scalar fields, vector fields can have sources and sinks, right? A vector is a thing that has length and direction, and of course, these lines of vector fields, they supposed to have some the source, right? So like this, for example. Yeah. So we call this source, and this is positive source, which means it's these lines of vector field go out from this source, and of course these lines can diverge to the point, and in this case it is a negative. I mean, in this case this is a sin, but we call this negative source. So it's a positive, and this is negative source. And of course, if I have more chargers, like 2 charges, for example, plus and minus, then these lines would be arranged like this. So they come out from the plus and sink to the minus. And of course, scalar field doesn't have this situation. The vector field has the sources, and how we describe the number of these sources, and the answer is that we use this concept of divergence. So how we describe the number of sources and sinks using divergence. Using divergence. So let's find the formula for the divergence. the divergence is the dot product of nabla operator with the vector field. So let's just substitute the formula for the nabla operator again. dz. So this is nabla operator, and for the vector field, we have components axi plus ayj plus azk, like this. And again, the all terms like I times j, I times k, j times k, j times I, etc. They all vanish because the vectors are orthogonal. And we get only three possible terms here, which are dax over dx plus day over dy plus daz over dz. And this is nothing but the formula for the divergence. So the divergence, nabla A, it's also denoted by this div A, and the formula is dax over dx plus day over dy plus daz over dz. Let's frame this formula. So quite important one. Like this. And let's consider maybe just a couple of problems for this formula. So problem one for the divergence. Let's consider a field, vector field with components xy, x squared, y squared, z squared, like this. What is the divergence of this field? Okay, so divergence of this field f is equal to the first term df. Let me step by step. If fx over dx plus fdy over dy plus df z over dz, right? And dfx over dx is equal to 2x, and the same for y, so it's 2y. So, and the same for the z, so it's 2z. Okay, so this is the answer, 2x plus 2y plus 2z. Again, divergence, the result of divergence is a scalar function, it's not vector, scalar. Problem 2. Let's consider something like this. Let's have exponential function. Let's take cosine here of y. I vector plus xy g vector plus z cube k vector. Again, the divergence of this field, first term by x gives us ex cosine y. The second term, not term, but the coordinate by y gives us x. And the third component z by z is given 3z squared. This is the answer. So next time we will continue discussion of the divergence, the flux of the field, and we will discuss the last operator, the curl. And I believe we will start the discussion of Maxwell equations. So this is it for this one. Let me stop the recording.